So next up, we have Henri Reggiani from Johns Hopkins University, who will talk to us about the chemistry of hypervelocity stars. All right.
Can you see my screen?
Yep.
Okay, great. So, hello everyone. My name is Henrique Reggiani, and I'm working at Johns Hopkins with Kevin Schloffman, and this work is based on data partially taken with the RCS spectrograph. So today I'm going to talk a little bit about chemistry of the hypervelocity stars, or where did the hypervelocity stars come from. So first, let's talk about what are hypervelocity stars. Back in 1988, Hughes was trying to find a way to prove the existence of the supermassive black hole in the center of our galaxy. And what he did is that he calculated what would happen if a pair of binary stars were to interact with such supermassive black hole. And he found out that in such an interaction, one of the stars would be ejected with velocities of up to 5,000 kilometers per second. And what he said is, if we find such stars with velocities exceeding 1,000 kilometers per second, it would be definite proof of the existence of the supermassive black hole. He continued his theoretical research in 1991 and 1992, publishing 2 papers in which he described different characteristics of such encounters, like the dissociation probability, the closest approach to either star, in which the intruder in this case is the massive black hole. And that was pretty much all the research in the topic until 2003. So when you get to 2003, you and Tremaine look back at this idea from Hughes and they try to find out details about different mechanisms that are related to this thing that Hughes proposed. So they calculated, basically what they wanted to calculate are the rates of hypervelocity stars being expelled in different propositions. So close encounter of 2 single stars, less than 10 to the minus 11 per year, tidal breakup of binary stars by the central black hole, 10 to the minus 5 per year. Things start to getting a little bit better, and 3 Body interactions between star and a binary black hole, in which one of the black holes is actually the supermassive black hole. And in that case, we can have rates as high as 10 to the minus 4 per year. And again, research on the topic stopped for another 2 years. 2005, almost 20 years after the initial proposition by Hughes, we actually found a star that was initially classified as a hypervelocity star. Brown was studying the velocity distribution of BHB stars in SDSS data, and he found among his sample 1 star with a 6 sigma deviation from the velocity distribution. This 1 star has a referring velocity of 709 kilometers per second, way higher than the distribution here, as it's pretty clear to see. And this is a null star, a young star traveling at extreme velocities. After the discovery of these first hypervelocity stars, people started going back and trying to study different mechanisms and seeing what can eject stars at such high velocities. So the first idea is, of course, the Hughes mechanism. People went back to things that were published even before Hughes. So ejection of a binary companion when one star goes supernova back to 1961. New propositions in 2009, tidal debris from a recently disrupted dwarf galaxy. So they can put together ideas from the 60s and from 2009, the dynamical ejection from the stellar clusters. Or even more recently, Bulbury and Evans studied ejections from the Large Magellanic Cloud, from the star-forming regions in the Large Magellanic Clouds. So all of these mechanisms can produce extreme and hypervelocity stars, but it's difficult to know where a particular star, how a particular star was accelerated to extreme or hypervelocity stars, hypervelocities. Okay, this is a review from 2015, and I think this is interesting because it shows the interest in this subject over the years. So these are the number of papers using the term hypervelocity stars. It starts in 1988, and we have pretty much nothing all the way to 2003 with that Ewan Tremaine paper. And from 2005, the research field kind of exploded, and now a lot of papers use those terms. And at this particular point, I would like to make an important distinction. So hypervelocity stars is a term that was coined by Hughes in 1988 to describe a star that was ejected with an interaction with the supermassive black hole in the center of our galaxy. So from now on, I will just use the term hypervelocity stars to describe these particular objects in which velocities can exceed 1,000 kilometers per second. But have we actually found these stars? Well, until 2015, we had about 20 stars, hypervelocity stars, but all of them are B stars. And because they are massive and young, we weren't so far able to tell which were the mechanisms that ejected them. Just they have very high velocities. We need some more information to be able to know which are the main mechanisms to eject stars to such high velocities. And then enters Gaia. With Gaia, we were finally able to find a lot of these stars because we have velocities, proper motions, and distances to 1 billion stars. In 2018, Hattori and Marchetti, trying to figure out what are these mechanisms where the hypervelocity stars came from, they tried to find hypervelocity stars in the Gaia data, but with one difference. They were only looking at low mass stars, because in low mass stars, we can measure chemical abundances. And if we have abundance patterns, that's an extra parameter that we can use to figure out where the stars are from and how they were accelerated to these velocities. But as you can see, none of them actually reached the 1,000+ kilometers per second threshold. So from now, we'll talk about this 500 to 700 kilometer stars as extreme velocity stars. Okay, and how does chemistry help us? As you can see in this plot, it is particularly useful to look at the abundance of alpha elements over metallicities, because at different galaxies, at any given metallicity, the alpha abundance can be quite useful to distinguish a star that was born in Fornax or the LMC or the Milky Way. And also in 2018, Hawkins tried to do this. They used RCS data collected in APO, and they tried to get the abundances of 4 hypervelocity stars from the Marchetti 2018 sample. And what they found is that the abundance pattern of these stars is similar to this purple and to the gray data here. And these are all Milky Way halo stars, normal Milky Way halo stars. Nothing special in their chemistry to tell us, to give us any more information other than they're halo stars. So what they conclude is that most of these stars are just the tail of the velocity distribution of the galactic halo. And then we also started collecting data. We collected data for 15 different stars. And what we see is actually quite different. So the diamonds and the pentagons in our plots are data from different dwarf spheroidal galaxies and from the LMC. Dwarf spheroidals here are Sculptor, Fornax, Carina, and Sagittarius. And what you can see is that at about metallicity of -1.5, you can really start to see a distinction between halo stars and dwarf spheroidal stars. And all of these extreme velocity stars appear to fall more in line with the chemical patterns of dwarf spheroidals than that of the Milky Way. And you can see that that is true for all of the alpha elements individually, and also if we use their mean ratio, the alpha abundances ratio. But is that true for the other elements? So we actually, with RC spectrograph, we can analyze elements from all the way from the alphas to neutron capture elements, and we can see that this difference also shows up if we look at light odyssey elements, for example, in which we can see that our stars are much more in line with data from dwarf spheroidal than that of the Milky Way, which stand right here. Great. What about neutron capture elements? Well, for neutron capture for the elements that we have data for in different galaxies and in the Milky Way, that is also true. As you can see here, our high barium abundances and our somewhat low and high ethium abundances, they are more in line with data with stars from different galaxies. So can we combine this chemical information that we just got with the proper motions and distances that we also have from Gaia and figure out actually where these stars came from? Well, we can try, and we did try. And out of these 15 stars here, combining metallicity, alpha abundances, and kinematic information, we can estimate probabilities of them belonging to different substructures that we see in our galaxy. We are using the probabilities from NIDU 2020 to make these calculations. And as you can see here, I do not include Milky Way halo, high alpha or low alpha, because all of our stars are either from a known substructure, like the Gaian Enceladus or Sagittarius, a substructure that hasn't yet been classified, or those that are the halo are the highest intensity retrograde halo. So what can we actually conclude from that? We haven't so far actually found a real low mass hypervelocity star. We haven't found a star with velocities exceeding 1,000 kilometers per second. But the extreme velocity stars continue to be extremely interesting objects, and their chemical pattern are clearly different than that of most Milky Way halo stars. So where are they from? They're from different substructures that are living in the Milky Way, or accreted galaxies. So our results favor that the most extreme velocity low mass stars are debris derived from dwarf galaxies. Thank you.
All right. Thank you, Enrique. Yeah, a very nice example of what you can learn from the Gaia data, as well as combining with other observations. So as usual, people can leave their questions in the Zoom chat or raise their hand. And while people are doing that, I'm going to ask another Gaia question because I'm very interested. To what extent do you think future Gaia data releases will expand because the radial velocities from DR2 only go down to relatively bright stars? And do you have a sense of whether your search capacity will be expanded by DR3 or DR4?
Well, I am not a specialist on Gaia data, so it's difficult for me to say about the radial velocities of Gaia, but it's definitely going to increase the samples that we have. For example, this data that we analyze here were gathered with DR2. And what I can say is that using DR3 data, it already has some significant changes in the final total velocities of our stars.
Okay.
But we do expect to find more as Gaia releases more data.
Okay, excellent. And I see Kevin has his hand up.
Henri, the idea is that Gaia Enceladus provided something like 70% of the Milky Way's halo, yet more than 50% of the stars in this high velocity sample appeared to come from something else. So is that in itself evidence of accretion from dwarf galaxies, or is that maybe reading too much into those classifications?
I think it might be reading, no. Okay, so the thing is that most of the stars here, they are at metallicities lower than -1.5. And Gaia and Enceladus, most of the stars that we know at in our alpha classification of that substructure is based on stars with somewhat higher metallicity. So the alpha distribution for lower metallicities at Gaia and Enceladus is not as well known as those for higher metallicity. So what can be happening is just that we're not entirely aware of the kinematic distribution, kinematic and chemical distribution of the lower metallicity end of that particular accretion event. That being said, it might mean that this is being overread, like you said, or it could also mean that these are actually from other accreted events. Personally, I do think it's more likely that these are accreted events from these are stars from smaller accretion events at from lower metallicity galaxies.
Okay, so I'll go ahead and cut things off there. Thank you again,